This section might be one of the most important lessons. We will see this for the rest of the year. We're going to see this with a couple of different, not just derivatives, but also integrals. And I see this all over the AP test. All right, so there's a couple of things. The function has to be continuous. It has to be on a closed interval, and it has to be differentiable. Those three things: continuous, closed, differentiable. If that is true, this equation applies. So what you have to understand is you'll have to find the derivative, you'll find the slope of 2 points, and then you will set them equal to each other. You have to look at this as separate pieces. So if we look at this figure on the side here, they're saying if you have any continuous function, and we look from one point to another point, if I connect those 2 points together and I find the slope using the slope formula, there is some point along through this interval in between A and B that the slope of this line will match the slope. It will be parallel to the slope of the tangent line. And then we're trying to look for what that x value might be to where the tangent line is parallel to the slope of the endpoints. Okay, so this just says, show that it satisfies the hypothesis. All right, first of all, is x squared, because that's our equation. What are the three things we have to satisfy? Continuous, yes, x squared is a continuous function. Closed, this is a closed interval. And differentiable. With all polynomial functions, they're always differentiable. If you're not sure, I would just write continuous, closed, differentiable. Then it satisfies this theorem. Okay, so first of all, it satisfies it. Then it says, find a solution C. So what we're going to do, we have to find the derivative. F prime of C, technically I'm going to say f prime of x is 2x. Take the derivative of x squared. We do this piece separate. Then we have to find the slope of the endpoints. All right, these are my endpoints. So do you see if I plug 0 into x squared, I get 0. If I plug 2, this is my interval along the x-axis from 0 to 2. When we plug 2 into the equation, I get 4. How do I find the slope of these 2 points? Is y minus y over x minus x. See, f of b is just my y minus my f of a, my other y, over my x minus x. So my slope equals 4 over 2, which is 2. So the question is, where are these two equal? Where does the derivative equal the slope of the endpoints? This occurs when x equals 1. So the solution C, when C is 1, this derivative will match the slope of the endpoints. So if I look from 0 to 2, this is the slope of these two endpoints. When x is 1, the slope of the tangent line is parallel to the slope of the endpoints. But when it asks you if it satisfies the hypothesis, continuous, closed, differentiable. That's what they want you to address. Okay, so This is asking us, why do the following functions fail to satisfy the hypothesis? All right. So if we consider the graph, the square root of x squared is technically the absolute value of x. Whenever you square root x squared, this has to be a positive value. We will never have a negative coming out. That's why we have to use the square or the absolute value. So what does this mean? At 0, what is this? This is a corner. If there's a corner in the graph, that means it is not differentiable at x equals 0. So because it's not differentiable at one spot, it fails to satisfy the mean value theorem. Now, so one thing that I would say, if I were to find the endpoints, say from -1 to 1, this is just a flat line, right? My slope is 0. The reason that we can't use the mean value theorem here, at a corner, it is not differentiable. There is no 0 slope anywhere on this curve. This slope would all be -1. This slope would all be +1. I could find all sorts of different problems. All right, letter B. Let's consider the graph. X to the third plus 3. 1, 2, 3. It's going to wiggle through here. I'm going to plug 1 in and get 4. So my x to the third graph looks like this, but this needs to be a hole, right? An open circle. And if I plug 1 in here, see, this goes all the way up through the point 1, 4. This one starts at the point 1, 2. And that's just going to be a parabola from the right side. Because it is discontinuous at x equals 1, it is not differentiable. Therefore, the MVT, the mean value theorem, fails. Okay. So just a couple of ways that it can fail. All right, number 3. Okay. Says find a tangent to f in the interval -1 to 1 that's parallel to the secant AB. So first of all, we have to talk about this particular graph. And sometimes it's helpful to understand, if we were to square both sides, I'd get y squared equals 1 minus x squared. Then if I move my x squared over, I get x squared plus y squared equals 1. This is actually just the top half, because it's not plus or minus, the top half of a circle with radius 1. And these are endpoints, because if I plug 1 in, I get square root of 0, which is 0. If I plug -1 in, so on this particular interval, that works. All right, so it is closed from -1 to 1. It is continuous and differentiable. There's no corners, cusps, anything funky, so it is differentiable. Okay, so first let's find our endpoints. We said this point is -1, 0, and this point is 1, 0. So what is the slope between these two is just 0 over 2, which is 0. My slope is 0. All right. Then we take the derivative of f of x. What's the derivative of the square root? 1 over 2 square roots times chain on the derivative of the inside, which is just negative 2x. The 2's cancel. I get negative x over. So this is my derivative. The question is, we need to solve for values of x that my derivative equals my slope. So when does 0 equal this equation? This is going to become very important. A fraction equals 0 when its numerator is 0. So this is basically telling me the point that this takes on, a 0 slope, is when x equals 0. So that would make sense because the top of that circle has a 0 slope, and that happens at x equals 0. Okay, so it actually wants the tangent line. So what is the equation of this tangent line? This is a 0 slope, which means it's a horizontal line. All horizontal lines have the equation y equals, what does y equal at this point? Y equals 1 is our final answer. So there's a lot of information here. First, we addressed the 3 pieces that it has to satisfy. Then we had to find our coordinate points to find the slope. Then we had to set the slope equal to the derivative. We found out that it happens when x equals 0. And then we had to find the equation of that line at the point x equals 0. So that one's kind of tough. All right. So the physical interpretation, I'm just going to say, let's just read through this. If we think of the difference quotient, this is, I don't like when they write it this way. We know this is how we find the slope. We also can call this the average rate of change, right? This is how we started chapter 2. We talked about the average rate of change is the slope of 2 points. The average rate of change, it's the slope of 2 points. It's also the slope of the secant line. It's the slope of the endpoints. That's what we've been finding. So the physical interpretation of your mean value theorem is where the slope of the secant equals the slope of the tangent. The mean value theorem is technically saying, where does the slope of the tangent line equal the slope of the endpoints, the secant? Okay? All right, so interpreting the mean value theorem. If a car accelerates from 0, if it takes 8 seconds to go 352 feet, 8 seconds to go 352, then its average is 44 feet per second, or 30 miles per hour. What this says is, at some point, from beginning to end, because this is saying from 0, 0, our starting point, to another point, the slope of these 2 points is 352 divided by 8, which is 44 feet per second, and we can convert all of this to get it into 30 miles per hour. Because we accelerated like this, at some point, the speedometer has to have read 30 miles per hour. They actually use this when doing your speed traps, using the cameras and calculating what the acceleration would have to be. Okay, so increasing, decreasing functions, this is important. I can guarantee you're going to find this a lot. So if f is a function on an interval I, we have 2 points, x1 and x2. Basically, this is saying that f will increase on I. So let me do a little chart. If this is x1 and this is x2, it's increasing if f of x1 is always less than f of x2, no matter where you're at on the graph. And on the other side, it decreases if the y value x1 is greater than the second y value. Okay? You don't necessarily need to know monotonic, but you will come across these. It just basically says you have functions that are always increasing or always decreasing. For example, all exponential functions, always increasing or always decreasing. They just give it a nice fancy word, mono, one tonic. Okay, so the corollary is what we're really going to use in this section. So think about x squared. So see how this is going down on this side? All tangent lines are negative. On the right side, it's going up. All the tangent lines are positive. So does it make sense? The derivative, the tangent line slope, is greater than 0 when f is increasing. So if it's going up, that means all of the derivatives have a positive value. If it's going down, all the derivatives have a negative value. Okay. Oh, we kind of just did that. Let me show you how I want you to write it though. And I'm going to show you kind of how to use some information. Okay, so we're going to find the derivative. The first thing we have to do is take the derivative, which in this case is 2x. We're going to set the derivative equal to 0 because 0 is going to be where it changes from increasing to decreasing or decreasing to increasing. So 0 is what tells us everything. So this happens at the point x equals 0. So we're going to create intervals. We always start with the interval negative infinity to infinity, and we just plug our values that we find here into and create intervals. So I'm going to go from negative infinity to 0, and then I'm going to go from 0 to positive infinity. I just insert the values we find from the derivative into the interval. And I'm going to look at, is the derivative positive or negative in that interval? Because this is where it's 0 slope. I want to find out what's happening before and after the 0 slope. So if I plug in what's a number that's in the interval negative infinity to 0, that would be negative 1. If we plug negative 1 into the derivative, that's negative 2. That's telling me the derivative will always be negative on that side. That means the function is decreasing. Then I'm going to plug a number that's in the interval, this interval, into my equation. So I'll pick 1. 2 times 1, that's a positive value. That tells me my function is increasing. So then we actually have to state this is not enough. You have to make a separate statement based on this, saying the function is increasing on this interval, 0. Oh, you guys, I'm losing my mind. Infinity always needs to be parentheses. From 0 to infinity. And the function decreases from, using this, negative infinity to 0. So we take the derivative, find where it does not exist or equal 0, create your sign charts, and then we make a statement based on our information. All right. Now, this particular one gets a little annoying, but this will be fine. We always start with the derivatives. You have to be able to take the derivative correctly. This is just our power rule. 3x squared minus 4. Then I'm going to set my derivative equal to 0. Since I'm just looking at x squared, I can get x squared by itself. So I'm going to add 4 to both sides, divide by 3, and then take the square root to get x by itself. Since I took the square root, I need to include the plus or minus of the square root of 4/3. So I need to use both of these, inserting them into the negative infinity to infinity interval. So I always start with negative infinity, then I pick my first value that comes up, the negative square root of 4/3. And then I'm going to go from negative square root of 4/3 to my next value, positive square root of 4/3. And then I'm going to go from this positive square root of 4/3 to infinity. Now, infinity always gets parentheses, even though I screwed up in the last example. Any place where the derivative equals 0 is included. We include these values. If it's where the derivative does not exist, if we come across one of those values, that's where we use parentheses, if it cannot exist there. All right, so I have 3 separate intervals. We're looking at f prime, and if I pick, so the square root of 4/3, that's maybe just a little over 1. So let's pick -2, plugging it back into the derivative equation. If I plug -2 in, -2 squared is 4, times 3 is 12, minus 4, that's a positive value. That tells me the function itself is increasing in this interval. All right, the best, any interval that contains 0, always use 0. In between the negative square root and the positive square root, we're going to use 0. If I plug it back in, I get -4. Negative means my function is decreasing. And let's pick +2, plug it back in, I get positive, which is increasing. Okay, now we just make a statement. Where is the function increasing? And increasing here and here. So negative infinity to negative square root of 4/3, union with square root of 4/3 to infinity. It is decreasing on this inside interval from the negative square root of 4/3 to the positive square root of 4/3. Now we have a bunch of just corollaries. So go ahead and just pause the video, copy down your corollaries. This is actually starting to get us ready for our antiderivatives. So going backwards from the derivative to the original. So it's just saying if a derivative is equal to 0, let's think about this. If we have a 0 derivative, that means there's a 0 slope. All right, so that's just saying that this had to have been a constant, like y equals 2. So it's saying if two derivatives equal each other, their original functions must only differ by a constant. So let me just show you for instance. Say that I have a function 3x plus 4 and a function g of x equals 3x minus 2. My derivative, f prime, is 3x, of 3x is 3, and g of x is also 3. So our derivatives are equal, but their constants are not. That's really what this is getting to. So when we're finding antiderivatives, we have to always account for the constants at the end. All right. So what we're going to do, it says find the function f of x whose derivative is sine. So if the derivative was sine, going backwards, what did I take the derivative of to get sine? The derivative of what is positive sine? That's going to be negative cosine. But there was some constant here that we don't know the value of. All right, so then they give us a point that we can plug 0 in for x, 2 in for y, and we can use that point to find the value of c. Now, what is cosine of 0? Cosine of 0 is 1. So 2 equals negative 1 plus c. So my c value is 3. So that means I can go back to this equation and finish the equation with negative cosine x plus 3. Final answer. All right. That's what we call an antiderivative. And that's really preparing us for the inverse of derivatives, which are integrals. So it's kind of already getting us started. Okay, so last example, finding velocity and position if we start with acceleration. So the first thing I want you to understand, it says find the velocity and position functions. Remember, S, V, A. We're now going to go backwards. It says A, let's just say of t, equals 9.8. It says a body falling freely from a height of 0 meters. That means the position of 0, S of 0 equals 0. If the body falls from rest, That means that our velocity starts at 0 as well. All right, so if I want to go backwards, my antiderivative, 9.8 would be the derivative of what? Constants, let's think about this. Like y equals x squared minus 4x plus 7. When I do the derivative, what do? We drop the exponent and subtract 1. If it's just an x, we just need the constant, and the constant goes away. So if we begin with a constant, the constant is the derivative of what? What was this original function? So if we're starting with 4x and the derivative is 4, that means to go backwards, if we start with a constant, we just add in the variable we're using. We always need a plus c. And then we're going to go back and use this information. Since f of 0 equals 0, my constant is 0. So if my constant is 0, then that's my original function for my velocity. All right, now I need to go one more step back to find the position. So think about when we're doing the power rule for derivatives, we multiply the exponent times the coefficient and subtract 1. So if we're going backwards, we're really doing the inverse. I'm going to take my exponent, this exponent here, if there's not one written, is 1. So going backwards, I'm going to add 1 to my exponent and divide. So this would be 4.9 plus c. We always need our plus c. So let's think about what I just said. When we do the derivative, we multiply and subtract 1. So when we're doing the inverse, what we're going to do is add 1 to the exponent and then divide. We're just going backwards. All right, since my position is 0, 0, that means my constant is also 0 for this equation. So here's my velocity function. Here's my position function. All right. Now, letter B, this is all letter A, sorry to tell you. Letter B said, what if we start with a velocity of 1? What if v of 0 actually is 1? How does that change my equation? All right, so we're still starting with a of t equals 9.8. So then my v of t, my velocity going backwards, the antiderivative of a constant, we just need to tack on our variable because the derivative of 9.8t is 9.8. The antiderivative of a constant, 9.8, is 9.8t plus c. This says v of 0 is 1. So my velocity is 1 at time 0. So my constant is 1. So v of t equals, I'm just going to replace 9.8t plus my constant of 1. Then I go backwards to my position function. So we're going to add 1 and divide. So 4.9 t squared plus antiderivative of a constant is just t, tack on your variable, plus c. The good news is we're still using s of 0. My position is still 0. So 0 equals 0 plus 0 plus 0. That means our constant is still 0. So my position function is 4.9 t squared plus t. Velocity function, position function. And that's it. Whew, lots of stuff.